Okay, in this video I will show how to make a solution to the differential equation that I explained in a different video. So we want a solution passing through an initial point. So I'm going to create a point, and then I need to see what is the slope at that point. So I'm using this differential equation, x plus y, and the number here is simply the calculation of negative x plus y at this point. If you recall, this is the point which we iterated, or we didn't iterate it, we made a locus of that point, and then we made a locus of the locus. So we need to do this again for this point. This will be the initial value for our solution, and I'm going to calculate the x value of that point, and I'm going to calculate the y value of that point. And then we will use this to make another calculation of minus x plus y. And this doesn't go with the x and y that I've previously defined, these two values, which we used to make the slope field, but this goes with the x and y of the new point that we've defined. So using that slope, I need to make similar calculations to similar to what I did before, increase the x by 1, so I'm increasing the x value by 1, and then I will calculate the y value plus the slope that we just calculated. And when I plot those two new points, which are very similar to these 2 points, when I plot these 2 points, I'll get another point. Now I'm off the side of the slope field. If I move it closer, I should eventually see my other point that I just created there. So I'm going to move it somewhere where I can reach both of the points. And while those 2 points are selected, I'll construct a line. And this line has the slope that the slope field shows should be there at point D. The differential equation dictates that the slope at D should be, if we pause right there, the slope at D should be this number, 1.09, and I've drawn a line through D that has the right slope. Now we're going to do the same thing we did for the slope field. I'll construct a circle with a given radius, but to make the radius I'm going to create a line segment, and I'll select that line segment and the point D, and I'll construct a circle by center and radius. And then what I want to do is, as I move D around, I want to create those 2 intersections between the circle and the line, and construct 2 small segments. I don't want to construct the whole long segment like we did for the slope field, which was 1 segment centered at D. I want to construct 2 short segments starting from D and going each direction. So I'll construct a segment there and another segment here, and then I'm going to hide the extra pieces that I don't need. Now this length will change as I move this. Now what we'll do is simply iterate D, and I can iterate it to a particular depth if I make a new parameter called, I'll call it n, and I'll say that we're going to go to 40. We can change that later, but this will be the depth to which we iterate D. So I'll click on D, and I'll click on n, and I'll say transform, and if I say transform and hold down the shift key, it gives me the option of iterate to depth. So I'll take that option, and I want D to go to one of these points. When I click on that point, I want to look at the structure and deselect, well, or I'll choose the non-point images only. I don't need all the points there, and it changed the appearance of that line very slightly. So if I went with all objects, I'll zoom in here, it looks like this with the little dots showing up. And if I change that to non-point images, non-point images only, the points themselves go away and I'm only looking at the segments being iterated. So I'll construct that, and what I would like to do is also construct, I would like to iterate it the other direction because I made this other segment, and so I'll say iterate that, and then as I move this around it follows a path here. Now you can see that there's kind of some spines sticking up on this. That's because when I iterated this point to there, I haven't named that point, it followed that, but then one of the children of D was this segment over here to the left of D. So it iterated that also, and I can just grab this whole image and I can just grab that whole image. Can't do it while I'm zoomed in. And delete that part of it. And I can also iterate D again. So I'll click on D and I'll click on the 40 again. And I will iterate to depth. And this time I'll iterate it the other direction. Click iterate. And I forgot to iterate the non-point images only. So I can click on the points and I can delete that part of the work. In fact, there's 2 points there. I can delete that, and now I only have the segments. Now what you'll see is that as I move this, I wind up with the same problem of those opposite segments showing up. So I can select those as a group and delete those. And now I should have only what I've wanted to iterate. And this follows, starting at a point, this follows the slope field in both directions and gives me a path where I'm always determining my slope using the differential equation given. Now to make this a good solution, I want to make this segment length quite small. So I can move this down. I'm looking at my segment over here that I created. I can move those 2 points very close to each other. I could also define this with a number, but I find this to be just fine. This is very effective. And I can use the arrow keys to nudge it into place so it's very close. Now this gets smaller as I get very close. These steps are very small, and there's 40 of them. If I wanted it to be a very smooth curve, I could make the steps that small. Visually speaking, I don't know if we lose a lot by making it a little bigger. You can see the curve shift as I increase it. I'm looking particularly in this area. As I increase the length of that segment, the curve shifts, and I know that the smaller the segment, the more correct the solution. But again, we would pay for that in the computer processing all of those extra calculations. So probably something like that is going to be good for our purposes. Now, if that's not a long enough piece of the curve, now is when I can change that value of n. I can change the value to maybe 300, and now whatever length my segments are, it'll give me 300 segments in each direction, and you can still find the end of the curve, but that probably would be as much of the curve as I need to look at. In fact, probably don't need 300, maybe 200 would be good. So I have a solution curve. One thing I want to do is I want to get rid of those 2 points to the left and right of D. So I'm going to temporarily make this segment longer and hide these. And then when I make the segment small again, it gives me a nice smooth curve. I can also select the whole curve and deselect the point and trace objects. And then when I move this around, it'll show all of the different solutions to this differential equation. And I'll be able to get a nice sampling of what this field of solutions looks like. So that's one way to create a solution to a differential equation. Now, there's one more note with this, and that is that when you change the slope field, these two things are now separate. So when I change the slope field, if I wanted to look at a slope field which was sine of x plus y, for example, there's my new slope field, but my solution is still working with this other differential equation that I defined. So I need to change this as well to say sine of the x value plus the y value, and then I can get my solutions to match up with the slope field, and I can see the solutions that fit into that slope field and go through it, pass through a certain point. I guess I'll just add to that this solution that we see here is not a true solution to the differential equation, but it's an estimate given to us by a method very similar to Euler's method that we teach in the first year calculus course. So Euler's method, we would be moving over in a set delta x. Delta x would be constant. Here, the length of our step is constant, so that if we're traveling, let's see, the length of that segment that we made was the same length everywhere we went. Every step was the same length. It's not the same. Delta x then changes according to how the slope changes. So the idea is very similar, and it's not the actual solution, but it's a curve or a path that looks very much like the solution and can give us a good idea of how the differential equation acts. So thanks for listening. I hope that's been helpful.